Good afternoon, ladies and gentlemen. I want us to continue with our lecture. Right. Last week we introduced memory management. We discussed the various techniques which are used by our operating systems in terms of managing how memory is going to be used within our systems. We also did memory allocation, and the last thing that I did, if my memory serves me well, was to do some computations or some calculations mapping our physical memory into our logical memory, and that was using the best fit, the worst fit, and the first fit. And according to my understanding, each and every individual, or should I say most individuals who attended the lecture, managed to understand, managed to get the idea of what we're trying to do. But today we need to continue. We want to continue with this memory management, and we need to touch on paging, right? So paging, we defined it last time as a memory management technique which is used to divide our memory into fixed slots or fixed pages. We covered that. But today, the most important thing that we need to do first is to appreciate how the page table, where do we locate our page table, what does it do in terms of mapping your logical memory and your physical memory, and then later on, we need to talk about a situation which happens when memory is addressing something which is not there in our physical memory. So what does it do? It will end up reporting what we call a page fault. Then when a page fault occurs, there's a set of steps that you need to do in what we call page replacement. You need to replace that page so that at least it won't give you the page fault rather. So this is what we need to do. But within the context of what I have on my screen right now is a situation whereby we have our physical memory here, right? Physical memory on one side. We also, logical memory, then physical memory. So this is our page table in between the two, logical and physical. What does the page table do? It maps your logical to physical. In other words, we're saying page 0 here is being mapped into memory location number 1 of your physical memory. This is page 2, but it's what? Memory location number 1, because we count from 0, 1, 2, and that particular order. Page 1, right, which was on memory location number 1 of our logical memory, according to the page table, we need to put it on memory location number 4. That's why you see this page 1 being taken to memory location number 4. The same applies to page 2. According to the page table, it's saying we need to take it to memory location number 3. You do likewise. This is a prescription, this 3 to 7, this is a prescription that we are being given by the page table. That's how you do it. That's what you follow, right? Then, going forward, we also need to know that memory protection is implemented by associating protection bit with each frame, and you indicate whether a bit is valid or invalid by using maybe one can use a 0 and a 1, or you can use I for invalid, then V for valid. This is just a way of indicating the presence, or should I say the presence of a particular frame or a particular bit in our main memory. So let me try to I'm going to use this one as our good example. I'm sure you will be able to understand. I skipped some slides for my own reasons there. Now, on our logical memory, we'll come back to this, but there's something that I want to highlight here. If you analyze this, you will see that according to the page table, memory location 0, where we have our A, right, is being mapped into memory location number 4 of our physical memory. What does that mean? It simply means that this is a valid bit, therefore you can take the contents of memory location 0 in our logical memory to memory location number 4 of our physical memory, because it's a valid bit. You remember the V and I, valid and invalid. Then if you look at the second one, our B, we find it in memory location number 1 of our logical memory. But according to the page table, you cannot find it on your physical memory. In other words, it's an invalid bit, and you are trying to map something which is not there in your physical memory. So it will give you an invalid bit. It can even give you a page fault. And where is this normally? If it's not in the physical memory, then definitely you find it in the baking store, right? This is a baking store. A baking store, or you can call it the secondary storage location. This is your hard drive. So it's not in the physical memory, you find it in the secondary storage. The same applies to 2, 6 is valid. I mean, contents of memory location number 2 of our logical memory are being mapped to memory location number 6 of our physical here. So you put your C. Those are the contents. D is invalid, 3 is invalid, so you get it in the baking store. All those with invalid bits, right? 6G, you find it in the secondary location. This is supposed to be G, not F, right? Then you have your 6, you have your 7H, H again, A, B, must be in the secondary storage location. Okay, we had A, B, C, D, E, F, G. Then A is valid, B is invalid, C is valid, D is invalid, E is invalid as well. Invalid, this is valid, then this is valid, then D is valid, then this one is not correct. Then you go to 6 with the G, we now have our G. Then H is invalid, you find your H here. So we only have 3 valid bits, that is 4, 6, 9. E, no, is 4, which corresponds to 0, then the 1 on 2, that's C, then the 1 on 5, that's F. So this is correct, right? I was trying to ascertain. Did you get that? Something which is invalid, definitely if it's invalid, you ought to find it in the baking store. But if it's valid, it's there in our physical memory. I don't know if it's making sense to you there. This is how you play around with it, with the so-called valid and invalid bits. Then this is just trying to explain the concept of swapping, right? You remember swapping, the technique of utilizing your secondary storage location for processes which are not going to be used like now, which are going to be idle for some time. You take them, or you swap them out. You swap them out to your baking store. You only take them back to main memory when you want to use them. So this is more like what? Your HDD in some instances, right? Your secondary storage location or your secondary memory. Just the idea of swapping, and I think you all know about it. So page fault, like I said, is more like an interrupt that is raised by your hardware, when a running program accesses a memory page that is mapped into your logical address space, the virtual space, right? But if you check on the physical memory, you cannot find it in the physical memory. Then it will prompt you with an interrupt. An interrupt is simply more like a signal for attention, right? So it's giving you that page fault. And it's arising upon a reference to a page that is not there in main memory. I think we rightfully explained that. And for you to remedy it, you now need to implement some replacement of page faults. So that next time when you try to reference, definitely you'll find it in your main memory, in your physical memory, right? So how do you handle the page faults? Let's say you want to load M, right? And what do you do with your M? You are trying to load M into your main memory. You check, even if you check on your page table, you discover that it's indicated by an I, meaning it's an invalid. Therefore, the operating system has to send an interrupt that is trap, right? It has to send an interrupt signal for attention. Now we need to find ways of correcting that. You cannot find it. You have sent your trap to your operating system. Now the operating system is looking for that page in the backing store in this area, right? It's trying to locate it in the secondary storage location, and definitely it's going to find it, because like I indicated, if something, right, which was written in your logical address space, if something is there and even the page table is indicating that, well, is there on the logical address space, but it's an invalid bit, meaning it's not there in the physical address space, what the OS does is to go and check from your backing store, right? This is more like the hard drive. This is the secondary memory, right? And once it discovers that particular M is definitely there in the backing store, you bring it back into your physical memory. Once you take it from the secondary storage back to the physical memory, you have managed to remedy the problem. But you are not yet done, because you now need to update your page table so that next time when you try to rerun the instruction, it won't give you an invalid bit. So you then reset your page table. So at the end of it, on your page table here, it won't be an I, but rather you are going to have a V, meaning it's a valid bit. Then you have managed to handle your interrupts in that particular order. Are we together? Now, going forward, we also need to do the actual replacement of these pages, right? How do we replace the pages? How do we replace the pages? You need to use the algorithms, various algorithms. And within the context of this lecture, or should I say of particular interest, is the first in, first out, the optimal algorithm, as well as the LRIO, that is the least recently used one, right? So whenever paging happens, paging happens whenever a page fault occurs and a free page cannot be used for allocation purposes, accounting to reason that pages are not available or the number of free pages is lower than the required pages. This is just the literature that you can go through, but of particular interest is to get the chemistry, or to get the set of steps that you need to follow when you want to replace a particular page. So first of all, you find the location of the desired page on the disk. Then you find a free frame. If it's there, you use it, but if it's not there, you now use the algorithm, a certain page replacement algorithm, to select a particular victim. The algorithm is going to give you a prescription on how you identify your victim, as you're going to discover. Then you bring the desired page into the newly formed free frame, update the page and frame tables, then you continue until you restart the instruction. So we now need to use this reference string here. This reference string, let me demarcate the reference string, this one, to implement page replacement using the 3 algorithms that I mentioned earlier on. Now, the first one, like I said, is the FIFO, first in, first out. This is the criteria that you use to replace any page that is not in the main memory. Now we've got a reference string 7, 0, 1, blah blah until you get to 0, 1 at the end here. Our objective is to execute this whole reference string. Now, within the context of our example, we are being told that we've got 3 frames. So we can only have 3 pages within our memory at one moment in time, right? The example is there on the next slide, but I want us to do it here together. Now, you start from here. Let me use blue. Draw your 3 frames. You now have 1, 2, 3. 7 is, we are trying to take 7 and see if it can give us a page fault or not. Because at the end of the day, you need to account for the number of page faults that you have, right? So take 7 into our memory location. You discover that 7 is not there. Theoretically, we agreed that if something is not there in the physical memory, then it means it's going to give you a page fault, right? So you're going to record a page fault here. Once you record a page fault, you now need to add 7 into your memory. You now have your 7. Then you take your 0. Again, it's also going to give you a page fault because our memory was totally empty. So you add your 0, you now have 2 page faults. Take your 1 into your main memory. Again, it's going to give you a page fault, right? And you put it inside memory. So basically, the number of pages, or should I say of page faults, yes, of page faults. You know, when you want to determine the number of page faults, you can easily say, okay, my memory was empty and I've got 3 frames, so I've got 3 plus page faults. You start from 3. It's also okay because definitely you are loading memory into an empty space, right? Or you are trying to reference from an empty space. Now we continue. We now want to load 2. It's also going to give us a page fault because 2 is not there. But so for us to execute this, we also need to know who is going to be the victim frame. You remember we said you need to select the victim frame here. How do you select the victim frame? According to FIFO, you use, or the victim is the one who came first. So we deal with the first frame which came into our memory. So the victim here is going to be 7. I think you agree with me. 7 is going to be the victim, and we replace with 2. Then we want to run 0. 0 is going to execute because it's there in main memory. You now want to run 3. It's going to give you a page fault, which is page fault number 5. And with the victim, 0 because he came first. So you cancel 0 and replace with 3. We are done with 3. 0 now, we want to execute, it's no longer there because we cancelled 0. We now have 2, 3, 1. 2, 3, and 1. So it's going to give us a page fault. Then who is going to be the victim? Who came first? It's 1. So we replace with 0. You continue like that. Let's run 4. It's going to give us a page fault. And who is going to be the victim? It's 2. Right? I need to change my color so that at least you can properly see. It's 2. We replace 2 with 4. Then you want to run 2, it gives you a page fault. Who is going to be the victim is 3, who came first, right? Then you want to run 3, it gives you a page fault. Who is going to be the victim? It's 0, who came first, right? Then you want to run 0, it gives you a page fault. Who is going to be the victim? It's 4, who came first. You want to run 3, 3 is there, executes. You want to run 0, 0 is there, it executes. You want to run 3 again, 3 is there, it executes. You want to run 2, 2 is there, it executes. You want to run 1, it gives you a page fault. Sorry, we are here. Let me change the color. We are somewhere there, right? We are here. Never mind the underlined 2. So who is the victim? Is 2. We replace with 1. And you also, did I add? You add here. You now want to run 2. It gives you a page fault, right? Who is the victim? Is 3. Who is here? You want to run 0, it executes. You want to run 1, it executes. You want to run 7, it gives you a page fault. Who is the victim? It's 0. We replace with 7. You want to run 0, it gives you a page fault, right? Who is the victim? It's 1, right? You replace with 0. You want to run 1 is not there, it gives you another page fault, right? Who is the victim? Is this one, this 2, you replace with 1. You are done because you have exhausted everything. So in other words, you have got how many page faults? 5, 10, 15. There are 15 page faults in this scenario. Which conforms to this, if you ask me? There are many ways of doing this. Some put my frames, they put the frames and, but the most important thing is to know that the victim is the frame or is the bit which came first. Then that is going to be our victim. Then we also have another condition that we call the Beladi anomaly. Beladi anomaly is basically adding more physical memory, right? Adding more physical memory. In other words, instead of having 3 frames, you might have 4 frames, right? You might have 4 frames, and with 4 frames, it's going to reduce the performance of your algorithm. In some instances, it might actually perform worse. Okay. Then, okay, I couldn't see my cursor, so I need to change the color. Then we go, this is just the same example. Here you could count as 1, 2, 3, 4. Here is an area where there was execution, or where the frame was there, the frame was there in our main memory. So we count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So again, this is our example where you have your 15 pages. Simple like that. Then the second algorithm is called the optimal. On the optimal, you replace the page that will not be used for the longest period of time. In other words, the victim is a page that is going to be offline for most of the time. Right? Now, I want us to use our example, not following this one, but how we were doing it within the context of our first example. You've got your 3 frames, right? And still we are using the same reference string. 7 is not there, page fault. Then you load your 7. 0 is not there, page fault. Then you load your 0. 1 is not there, page fault. Then you load your 1. So you have got 701 in your main memory now. 2 is not there, That's another page fault. But who is the victim now? The victim is 1 among 701 that we have here, who is going to be offline for most of the time. Right? You discover that 0 is going to be online soon. Then 1 is going to be online soon as well. So 7 is going to be offline. So this is our victim. You replace with your 2. So your reference string is now 201. You now want to run 0, it executes. You want to run 3, page fault. Right? Who is going to be the victim? 1 who is going to be offline for most of the time. 201. Let me write it again, rewrite it again in that order. So who is going to be offline for most of the time between 201? 0 we are going to use just now, even 2. So 3 is the victim. Sorry, we are using 201, 20, then 1 is somewhere here. So 1 is our victim. We replace 1 with our 3. Now, you go to the next one, 0, it executes. 4 is going to, we are going to have a situation, it's not there in our main memory, so it reports a page fault. But who is going to be the victim? 203, so it's 0. You replace 0 with your 4, right? So you now have 243, right? 243. Then 2 is there in main memory, so it executes. 4, we now want to put 3, it's also there, so these ones are executing, yes. Right? Then 0 is not there. Who is going to be the victim? 243, 3, 2, 4. So 4 is going to be the victim. We replace 4 with 0. You now have 2, 0, 3. Oh, I forgot to record the page fault. Right? Then 3, it executes because it's there in main memory. 2, it executes because it's there in main memory. 1 is not there. Who is going to be the victim? 203. So I record the page fault, then locate the victim. The victim 203, 2 here, 0 there, 3 is not there. So 3 is going to be our victim. So we end up with 201. Then 2, it executes. 0, it's also there, it executes. 1 is there, it executes. 7 is not there. So who is the victim? We've got 201, 01. 2, we cannot find it. So 2 is our victim. You replace with 7. So you now have 7, 0, 1. Right? Then 0 is there. I forgot to record the page fault. Right? Because we said 7 is not there. So you add it there. Then 0 is there. 1 is there. So how many page faults do you have? 1, 2, 3, 4, 5, 6, 7, 8, 9. It's also confirming to this one, 5 plus 4, which is equal to 9 page faults. Right? That's your optimal algorithm. It's looking into the future. Now, there's a direct opposite, a mirror opposite of our optimal page replacement algorithm, which is the least recently used. Now, instead of looking at into the future, you use the past rather. You use your past knowledge to decide the victim, who is going to be offline for most of the time. Right? Again, I'm going to use our the 3 frames. Right? 1, 2, 3. 7 is not there, page fault. Right? Then you load 7. 0 is not there, page fault. Then you load your 7. Then 1 is not there. You load it because it's also recording a page fault. So these are all page faults. Then 2 is not there. It's also recording a page fault. But who is the victim now? 701. We have got we want to replace with 2. Want to replace 2. Between 701, who has been offline for most of the time, it's 7. So 7 is gonna be our victim. We replace with 2. Then 0, it's there. So no page fault, it executes. 2. No, this is not there. Then 3, we're going to have a page fault. But who is the victim? 201, 02, so it's 1. We replace with 3, right? So you now have 203. Then 0 is there, it executes. 4 is not there if you check. So who is going to be the victim? 203. 203 is 03, so it's 2, right? You replace with 4. Then you record your page fault. Then 2, page fault. Who is going to be the victim? 403. 403, so it's going to be 3, right? You replace with, you replace your 4, you replace your 3 with the 2, right? Then 3 is not there. That's a page fault. These are all page faults. 3 is not there. Who is the victim? 402. 0, right? Because 0 is going to be offline most of the time. You replace with 3. I need to indicate the page fault here. Then 0, page fault again. Who is the victim? I think I added some certain page faults twice. Like when we get here, I don't need to add. Because we did with 1, 2, 3, 4 page faults. This is not a page fault, but I had recorded. So the next page fault, I don't need to record. Then 3 is there in main memory, so it executes. 2, here we didn't replace our 4. Isn't it we said 0 is not there? So who is the victim? It's 4, because 4 is going to be offline as compared to 2 and 3. Then when you continue, 0, you now have 0, 3, 2. You now want to load 3, it executes. 2, it executes. 1. 1 is not going to execute because it's not there in main memory. Who is the victim? 0, it's 0. So you replace with 1 and you add your page fault like I did. Then 2, it's 2, it's there, it executes, right? Then 0, it's a page fault. Who is the victim? We had 1, 3, 2, 1, 3, 2. This is 1, isn't it? 1, 3, 2. We have got 2 here, we have 1 here, so 3 is the victim. Right? We replace 3 with a 0, so that we remain with 1, 0, 2. Right? Then 1 is there, it executes. 7 is not there. Who is the victim? 0, 1, 0, 2, 1, 0. So it's gonna be 2, right? So since there is a page fault, you record it, and then you replace your 2 with 7. Then 1 is there in main memory, it executes. So how many page faults? 5, 10, 11, 12. You've got 12 page faults. That's your LRIU. So at the end of the day, you also need to know the one which gives you the best performance. LRIU, we had 12 page faults. The optimal, we had 9 page faults. Then the first come, first serve, we had 15 page faults. You can decide which one is the best there based on that information. Thank you for your attention. The next thing that we need to do is to discuss file management, how files are managed within our systems. Then we take it, we see